Welcome back, Franken friends. I'm Greg Smith, aka Dr. Francintosh. Have you ever wanted to render directly to the HDMI on your Raspberry Pi 02W? Well, you used to be able to. Now, the Raspberry Pi has an operating system, Raspbian, and it has a desktop, but the 02W just isn't powerful enough to run the desktop and any program you want to create. So sometimes you want to render directly to HDMI, like I did on my Pi Mirror project, which you see over my shoulder. So you want to write directly to what's called the Framebuffer. But most of the Python libraries that do graphics no longer write to the Framebuffer. People just don't do it anymore. So the only way to do it is to do it in C on the bare metal. But if you're a Python programmer, you're kind of out of luck. Well, today I'm going to show you how to do just that. We'll write a C interface to the Framebuffer that renders directly on the Framebuffer and gives you bare metal speed using Python. But first, please don't subscribe to my channel. Don't like this video. Don't click up there or over there. Your time's precious, so please don't waste it on anything I'm doing. But as always, thank you so much for spending part of your time with me. Now, let's get to it. So before we get started, let's talk a little bit about how Framebuffers work. Now, if you have an HDMI display, which is 1920 by 1080, every pixel on that display has a different color, and it's represented in Framebuffer memory by 2 bytes. And those 2 bytes then are 16 bits, and they represent red, green, and blue hues. And the red, green, and blue are typically in the Raspberry Pi 5 bits of red, and then 6 bits of green, and then 5 bits of blue. So that means there are 32 different values or hues for red and blue, and then 64 hues for green. And the reason why green gets extra values is because our eyes are actually a little more sensitive to green than red and blue. So values from 0 to 31 for red, 0 to 63 for green, and then 0 to 31 for blue. And also, there are 1920 by 1080 pixels, which is over 2 million pixels, times 2. So we have over 4 million bytes that we have to transfer from memory to the Framebuffer in order to see our image in the Raspberry Pi. Now, the pillow library that we're going to use for doing line drawing and text drawing in our bitmap memory does not use RGB 565. It uses RGBA, which is red, green, blue, and alpha. And the alpha channel is for opacity, and we're not going to use that at all. But the problem is that RGB is 8 bits of red, 8 bits of green, and 8 bits of blue, 1 byte for each pixel. And we have to somehow transform that 3 bytes into the 2 bytes that the Framebuffer expects. And basically, it's a bit of bit-twiddling. And Python, as powerful as it is, just doesn't do that very well. It's going to have to go byte by byte and recombine all the RGB bytes into a packed RGB 565. And the reason why this RGB 565 is used is to keep the Framebuffer memory low, because it's actually a piece of hardware. What we'll do in the code is first we'll walk through this using Python, and I'll show you how fast, or actually how slow it is, and then we'll do it again, only we'll do it in C. So let's go do that now. Okay, so let's get started. So I've created a little bit of a dummy program here called Main. Down here you can see where it gets started. We instantiate Main, and then we call run. When we instantiate it, it prints out initializing main class, gets our arguments, and then prints them out. And then finally, we create our screen that we're going to do our rendering on. Now, to do this, we need to send this over to the Raspberry Pi. This is all happening on my Mac. So what I do on the Mac is that I have a script running, which will constantly check to see if there have been any changes to the code. And if they have, it pushes it to GitHub. And then over on the Raspberry Pi, we can do a git pull and get the latest updates. So we'll just do a git pull. Okay, and then what we'll do is we'll call build.sh, which will create our virtual environment. activate the environment, and then pull any requirements in that we need. And then we'll do a run.sh, which just sources our environment or activates our environment and then runs the main project. And as you can see, it says initializing main class, arguments, and then also running main class. Now mind you, whenever you see this colorful prompt down here, this green and blue prompt, this is running on the Raspberry Pi, which I have running on the Francintosh project that I built earlier this year. So that gives us a way of editing on the Mac, but running on our Raspberry Pi. So again, we have just the framework of the screen object. It creates a screen config and assigns it to underbar screen. Now, if you remember in Python, members of a class that begin with underscore are kind of hidden, so they're not to be called from outside the class. We have our debug flag, and then we call our own local print function, which checks to see if the debug flag is either true or false. So let's go back and add the debug parameter. Let's turn that in. Debug equals not self args quiet. So if it's not quiet, then debug is turned on. Okay, and so now that we have debug turned on, we can see the debug output. And if we ever want to run this with debug turned off, we can run it with -- quiet, and debug is turned off. All right, so now let's do the first obvious thing, and that is let's write to the frame buffer and clear it out. So let's do what I would call a hard clear. So hard clear takes in a color byte and writes it directly to the frame buffer. So here you can see frame buffer is equal to /dev/fb0. So down here we open screen frame buffer for write binary as f, and then we f.write whatever the color is times the screen width times the screen height, and it writes these bytes directly to the frame buffer. So if you don't specify a color, it writes zeros, which means black. So let's give that a try. Okay, so you can see that it cleared the screen, and it's actually printing our debug. So let's turn the debug off. So we'll specify -quiet. There you go. And now you can see it's running the main class. And there you go. Now, how do we know this actually worked? Well, let's try a different color. So we'll try white, which would be all bits on, which is FF, FF. And now you can see the screen is white. Let's try again with a different color. Now, mind you, in order to make this work, we have to specify the RGB colors that the frame buffer expects. It just happens to be 5 bits of red, and then 6 bits of green, and then 5 bits of blue. So I just happen to know the colors, and if we do F100, that's going to be a blue background. So let's watch that. So for green, that's going to be 7E0. And so that would be F10000. So this should be red. Remember, what we're doing here is we're writing directly to the memory of the frame buffer. And what we're putting in the exact same byte over and over again. So we are able to specify red, green, and blue. But what we really want is to address each individual pixel. And that's a lot harder. Now to do that, we're going to use the pillow library. And a pillow library gives us the ability to create bitmaps that we can render on. And so let's do that. Let's pull in the pillow library. So we're going to create a bitmap, which is the same width and height as our screen, in the RGBA format. And the RGBA format is red, green, and blue, plus an alpha channel, which is for opacity. And eventually we're going to have to rearrange these bytes to fit into the 565 RGB frame buffer. And we need to get a draw object so that we can actually draw lines and such. So that's the first step. Now that we've got a bitmap, we need to render it onto our frame buffer. So here's our frame buffer renderer. Now, mind you, when we write to the frame buffer, the memory that comes in the bitmap is in a different format than the frame buffer. Remember, the frame buffer is 16 bits. 5 bits of red, 6 bits of green, and then 5 bits of blue. So we need to take these basically bit planes of red, green, blue, and alpha channel and rearrange the bits so that they fit in our RGB frame buffer. So we're going to write each pixel of the frame buffer 1 pixel at a time. We're going to go row by row and then pixel by pixel within that row. And we're going to create a byte array in Python that represents the frame buffer that we want to write to. Row by row, from 0 through the height of the bitmap. And then each pixel within the bitmap, we pull the pixel out, we rearrange it so that it's 5 bits of red, 6 bits of green, and then 5 bits of blue. And then we organize that so that the 5 red bits are at the top, the 6 green bits are in the middle, and then the 5 blue bits are at the bottom. We then extend that array with those 16 bits. And we do this for every pixel. Notice that as we move along, I'm actually printing out the number of the row because I want you to see just how long this takes. And then finally, we write all those bytes out to the frame buffer so that they display. So when our bitmap is ready, we're going to write it to the frame buffer. So we have to update our main code, and then we're going to start off with a white background, and then we're going to write the new frame buffer out. Remember that we've reset the frame buffer to 0. So what should happen is we start off with a white background because we cleared it, and then we're going to flush the new bitmap, which is our backing bitmap, to the frame buffer, and it should turn black. Let's watch that. So I've turned off quiet, so we'll get our debug output. So it's going to reset the frame buffer to white, and then we'll immediately start writing the frame buffer 1 line at a time. And you can see what's happening here. It says it's converting row 150 out of 1080. Look how long that's taking. And what we're trying to do here is clear the frame buffer. All right. So it reset the frame buffer to all black. It would be more interesting if we could actually see it draw something. So let's do that. Let's add some functions for drawing lines and rectangles. All right. So what I've done here is I've added a line function. It prints out that it's drawing a line, and then it calls the pill line draw function. And the only reason why we've extended this is so that we can work with our screen object instead of having to call draw directly. Likewise, here's the rectangle function. And back in our main, we call a rectangle starting at 1010 to 1910 to 1070 of red. So we've got a red rectangle, and then a green line through the middle of the rectangle, and a blue line through the middle of the rectangle. And then it flushes it out so that we can see it. So let's go ahead and run that now. So once again, it cleared the screen to white using our hard clear function, and it's now converting each row from our bitmap into the frame buffer format. And it is taking a very long time. But once it's done, it'll write the entire frame buffer to the display. Okay, and there you can see our red box with our blue and green crosshatch. So now what we're going to do is do the same thing to convert the Python bitmap into the frame buffer format, but we're going to use C. So to do this, we have to wrap our C function in what's called a Pi object. It's going to pass in a Pi object as well as some arguments. It's going to do our RGBA to RGB16 in C. And so down here, we get our width and our height, which are passed in from the arguments. You can see here, we're parsing the arguments. We're getting RGBA, we're getting our data length, we're getting our width and our height. So we compute the entire size of the frame buffer. We allocate enough memory for the frame buffer. For each byte in the bitmap, we grab the red and the green and the blue, and we recompute it by shifting it around, and then add it to our output frame buffer. And when we're all done, we take pi byte from string and size, and it will convert it into a Python object. It'll free the old memory and then return the result. So if you look at our code from our Python, it's very similar, right? We grab the red, we grab the green, we grab the blue, We shift the bits around, and then we add it to the memory. And then finally we write it out. And in the C version, we do the same thing. We grab the red, the green, the blue, we shift the bits around, and then we add it to the output frame buffer. Now, in order to call this C function from inside Python, we're going to have to do a little bit of setup. So this little setup function says that we are creating a C library. This is the name of the function that we're creating, or the name of the module that we're creating, and it comes from clib.c, and this is the name of it, its version, our description, the module, that's the module that we're using, and whether it's zip safe. Now, back in our build script, run Python setup, and it will build this for us. Again, I'm running remotely on the Raspberry Pi. All right, so now and you can see the clib cpython arm.so. This is a shared object, and so this is the thing that we are now using when we call our function. We have this fast write frame buffer, and we need to import our C library and get our RGBA to RGB565. So we get our frame buffer, we import our RGBA to RGB16, we get our raw image bytes, we call our C function, we open up our screen buffer, and we write to it. And down here in our flush function, we're going to add a check to see if we're using fast flush or slow flush. So now you see here we have a check for fast flush, and if there's a fast flush, we write the frame buffer using the fast write, otherwise we use the slow write. Then up here is set. So let's try running our frame buffer test program with dash quiet on so we see no debug output. As you can see, it flashed white and immediately printed our box plus our cross. Now, just for fun, I've added some text. So there you have it, writing to HDMI through the frame buffer with Python using a C extension. Really, it was the only way to make Python performant enough to be able to build the PyMirror dashboards. It's actually gotten me excited about writing C on the Raspberry Pi 02W, and my next project, which I hope to show you soon, is a complete bare metal application running on all 4 cores of the Raspberry Pi 02W, including keyboard and mouse, and Wi-Fi and SD card. So I'm very excited about using bare metal applications, and I think you will be too. So please, as always, thank you so much for joining. Don't like this video, don't click up there or over there. Your time is precious, don't waste it on anything I'm doing, but always, thank you so much for joining me, and I'll see you next time on Dr. Francintosh.